In this lecture, we will discuss about the pressure distribution on an airfoil, and further we will discuss about airfoil nomenclature and airfoil characteristics. So, in the previous lecture, we had discussed about the concept of center of pressure, and we also discussed about the geometry of an airfoil. So, we very importantly introduce the concept of camber. So, we will revisit that concept once again, and we will now introduce the concept of symmetric airfoil in addition to the cambered airfoil that we already looked at. And then we will see how the pressure distribution on these airfoils would look like when the angle of attack is 0 or otherwise. Now, in symmetric airfoil, the camber line superposes on the chord line. That means, you essentially do not have any camber, and therefore, when you equally distribute the thickness about the camber line, which is nothing but the chord line, the thickness is symmetrically disposed about the chord line. So, this is like a uniform flow approaching a symmetric airfoil, and you can now understand that to the flow this geometry will look absolutely symmetric about the chord, and therefore, the streamline pattern will be identical above and below, or rather kind of mirror images, and that would end up producing identical pressures on the upper and lower surface corresponding to a particular x by c. What that means is that you do not have a pressure imbalance between the upper and lower surfaces of the airfoil, and this consequently would mean that this will end up producing a net 0 lift. On the other hand, in the case of a cambered airfoil, of course, we know that there is a non-zero camber, and then once you distribute the thickness above and below the camber line, you end up getting the airfoil shape, and the shape certainly looks asymmetric about the chord, and that is how it is visible to the flow as well. And therefore, when the flow moves around this surface, the streamlines are asymmetric. Consequently, the pressure distribution is also unequal on the upper and lower surfaces at any given x by c. If you take care of this pressure imbalance, which is largely the variable which influences lift, the lift becomes non-zero even at an angle of attack of 0 degrees. So, at an angle of attack of 0 degrees, lift is 0 for a symmetric airfoil, while lift is positive for a positive cambered airfoil. What we mean by positive cambered airfoil is that the camber line is above the chord line. If incidentally the camber line was below the chord line, that would have led to a negative camber. For example, if this is a chord line and the camber line has moved below, this is an example of negative camber. However, we are not bothering about that, we are bothering about a positively cambered airfoil, and it ends up giving us a non-zero lift, which is positive. Now, we would be interested to see, of course, how the pressure distributions really look like in principle on the upper and lower surfaces of the airfoil. One interesting thing is that if we are interested to look at the thickness of the airfoil and probably identify a location where it has maximum thickness, then it is easier done on a symmetric airfoil, because you can identify the thickness change along the length of the chord line much easily over here because of the absence of camber. So, one may say that by careful observation that this may be the location of the maximum thickness. So, wherever the highest ordinate values are obtained for the upper and lower surfaces in terms of magnitude, that is where the maximum thickness would be obtained. So, you can say that that is T max, maximum thickness. There is also a location corresponding to that, you can say x by c T max. So, that is the x by c value where the maximum thickness actually occurs. Now, as we said that we would like to have a look at the pressure distribution. Let us try to make some plots to understand how it looks like. What happens is that when the flow approaches the airfoil, when it is coming close to the leading edge at alpha equal to 0, you get a stagnation point. What does that mean? Where the local velocity becomes 0. We discussed it in the context of the pitot-static tube in a previous lecture. We had talked about a stagnation streamline and a stagnation point at the orifice, at the end of the orifice, which was facing the flow directly. So, the leading edge of this airfoil has a similar stagnation point where the flow goes to a 0 velocity, and consequently the pressure coefficient, if you consider it to be defined by incompressible flow, will be given by this expression which we studied earlier, and therefore, C p becomes equal to 1 whenever you have stagnation. So, if you are not considering viscous effects and additionally you are considering inviscid incompressible flow, then that is how it works, that the peak value of C p will be 1. When we plot the C p distribution, we usually plot the positive values below and the negative values above. This of course gives you the x by c side, and on the y axis we are plotting pressure. So, the leading edge is where C p equal to 1 is obtained, and then the flow very rapidly expands or rather accelerates, and then gradually decelerates. The pressure may come down later on as it approaches the trailing edge part of the airfoil. So, this is the stagnation point where C p has gone to a value of 1. Then there is a very rapid acceleration in this region where the flow is accelerating because of the upward sloping surface. Then it kind of gets flatter and then gradually slows down. So, depending on the shape of the airfoil, this part can take different shapes. It depends how quickly it is accelerating and then how quickly or how slowly it is decelerating, that these particular shapes will be governed. So, these are functions of the shape of the airfoil. Shape of the airfoil would determine the exact nature of the Cp versus x by c plot. This is how we call this or name this plot. But nevertheless, we are interested to broadly understand the features. So, we should have a stagnation point at front, very rapid acceleration, because of which the Cp becomes negative, because according to this equation, as u becomes large enough and it exceeds u infinity, you know that it goes below 0. So, this is Cp 0 and anything above is a negative Cp. That means, u exceeding u infinity will create a negative Cp. Because of the rapid acceleration, there is a negative peak which is created, which is the region where highest extent of acceleration has occurred, and then it starts gradually slowing down as it approaches the trailing edge of part of the airfoil. This is broadly the nature of the Cp curve. And if you were to plot both the upper and lower surfaces, upper and lower surface Cp distribution is identical. That means, they merge on each other. Now, if you were having a gap between them and then you had an enclosed area between them which could be integrated along the x by c direction, that would have given you the effect of lift coming from the pressure difference between the upper and lower surface. You would have a positive lift if there is a lower pressure on upper side and higher pressure below, but that is not happening here, and therefore, lift will be 0. So, the area enclosed within the Cp versus x by c plot. So, the area enclosed would be basically the region lying between upper and lower surface Cp, and here that area is 0 and hence the lift is 0. That means, if we were to go to a cambered airfoil where the pressure is different between the upper and lower surfaces, you would get an area enclosed, and if you integrate it, you will get the lift contribution coming from there. We will follow the same conventions here too, and then in principle you would get this negative peak on the upper surface, but it will be stronger because of the effect of camber, and on the lower side the stagnation point will not be exactly at the leading edge, it may be slightly offset. This offset becomes larger with increase in angle of attack. That means, as you go to positive angles of attack, you would find that the stagnation point is not exactly at x by c equal to 0 anymore. It is shifted from x by c equal to 0 to a small positive value. So, in principle, this suction peak again occurs, but it is going to be a little stronger because of the camber, and then it will drop as usual. But on the other side, you may have a slightly different pressure distribution, maybe somewhat like this. And then the main idea is that you have an enclosed area between the two, and if you integrate that, you will get the effect of lift coming from a pressure difference between the upper and lower surfaces. So, the one which goes to a stronger negative peak is the upper surface, and which remains below is the lower surface. This enclosed area is going to increase with increase in alpha. It is going to get expanded further with increase in angle of attack, and it is true for both symmetric as well as cambered airfoil that this is going to increase. However, the only difference is that even at alpha equal to 0, you do see a gap between the two plots for the cambered airfoil because of the asymmetry about the chord line, which you do not see in the case of a symmetric airfoil. The streamline patterns or streamlines in general become asymmetric due to camber and also as alpha increases. So, there is no asymmetry for symmetric airfoil at alpha equal to 0. The streamlines are symmetric for a symmetric airfoil at alpha equal to 0 degree. Why we said that with increase in angle of attack, the stagnation point may move to the lower side is because with increase in angle of attack, the free stream velocity approaches the body like this, and the stagnation streamline basically meets the body somewhere here. Streamlines above it move towards the upper surface of the airfoil or the leeward surface, and the ones below the stagnation streamline move to the lower surface. Consequently, the stagnation point moves to this region, and as you can see that in terms of x by c, now there is an offset between the leading edge and where the stagnation point is. So, this is not going to be x by c equal to 0, that is for the stagnation point. So, that is as far as the pressure distribution and the nature of the flow is concerned for a symmetric and asymmetric airfoil at alpha equal to 0 and non-zero alphas. Let us now discuss a bit about airfoil nomenclature. We will discuss mainly about NACA series of airfoils, which are a very widely used family of airfoils. And one of the first to be developed systematically in the early days, mainly through internal testing. To begin with, we have a 4 series airfoils family. The nomenclature looks more like NACA, and then there are 4 places to fill in terms of numbers, single digits to be filled. The first digit that you need to fill, what does it represent? It represents a maximum camber in hundreds of chord. That is the first digit. What is the second digit? The second digit, it gives you the location of the maximum camber in tenths of chord, and the last two digits in a combined way, what do they tell us? They give us the max thickness, the maximum thickness in hundreds of chord. So, as an example, if you pick up say NaCa 2412, so you have filled up the 4 digits. So, what that would mean is that you have a max camber of 0.02 C, because it is in terms of hundreds of chord, 2% of chord. That means location of the maximum camber is max camber location, that means where the max camber occurs is 0.4 C, and that is from leading edge. So, if you go 40% of the chord, that is where you find the maximum camber, and the maximum thickness of the airfoil is 12% of the chord, because it is indicated in terms of hundreds of chord. So, that is the nomenclature we follow for 4 series airfoils. Subsequently, there came 5 digit or 5 digit series of airfoils. In that case, of course, as you can understand, you would have 5 places to fill in terms of numerics. So, the first digit, you have to take the digit and multiply it by 3/2, and then you get the so called design lift coefficient. Once you do that, what does that mean? For understanding the design lift coefficient, we will make a very small sketch over here. So, we are just looking at the leading edge of a cambered airfoil. So, this is your chord line, this is your camber line, and what you are doing is you are looking at the slope of the camber line at the leading edge. So, this is approximately the tangent to that camber at the leading edge. This is your leading edge point, and then what you are saying is that your free stream, if it is approaching parallel to this tangent, that means that basically defines your angle of attack. At that angle of attack, if the free stream is approaching this airfoil nose, you would have a theoretical lift coefficient corresponding to this angle of attack. This is basically based on inviscid theory. So, that is what is called as the design lift coefficient, the theoretical lift coefficient which will occur under this situation. So, if you multiply the first digit by 3/2, you get that value. Going to the next digit, what does the second digit tell us? Rather, we would actually have to look at the next two. So, the next two digits, when divided by 2, gives the location of max camber from leading edge in hundreds of chord. The final 2 digits give the max thickness in hundreds of chord. So, if you pick an example, say NaCa 23012 for example, then what do you get out of it? You get a design lift coefficient equal to 0.3 by following this step. Then you get location of max camber is 0.15 C and max thickness is 12% of chord, often called as 12% C. So, this is the 5 digit series, and there is one more in the NACA series, that is a 6 digit series as well. Six digit, we will write down an example straight away, say NaCa 65-218. The first digit represents the 6 digit series itself. The second digit, what does it give? It gives the location of minimum pressure in tenths of chord from leading edge, considering symmetric thickness distribution at 0 lift. That means, even though it has a camber, we consider the symmetric thickness distribution at 0 lift, and then the corresponding location of minimum pressure in tenths of chord from the leading edge is represented by the second digit. And then the third digit gives you the design lift coefficient, which we have already discussed in the context of the 5 digit series. In tenths, and the last 2 digits, what do they represent? They give the maximum thickness in hundreds of chord. So, in terms of this airfoil that we have as an example, what would the values come out to be? The 6 digit of course represents the series, as we have already mentioned. The minimum pressure occurs at 0.5 C, the design lift coefficient is 0.2, and the airfoil is having maximum 18% thickness. So, that is what we can infer from this nomenclature. So, these NaCa airfoils were predominantly designed based on wind tunnel experimental data starting from about 80-90 years back, and then there were modern developments too. In the 1970s came a significant development of the NASA NASA low speed airfoils, which were particularly more efficient for general aviation aircrafts, they had a flatter leading edge, a flatter upper surface, a flatter leading edge would obviously mean that the leading edge radius was made larger, and they had a kind of a cusp, as we say, cusp trailing edge to increase the camber closer to the trailing edge without making most of the upper surface too cambered. This helped in improving the performance of this airfoil substantially over some of the existing NACA airfoils, and consequently what happened was about 30% higher CL max was obtained. What is CL max? We recall that in the CL alpha curve, the highest point that the CL curve reaches is called as CL max. So, there was about a 30% improvement on that, and then approximately 50% increase in L by D ratio at a CL value of 1. So, let us say if the maximum CL that this airfoil is generating is about 1.6 say or 1.5, then a CL value of 1 will be somewhere here. So, at that CL value there is an increase of the L by D ratio by 50%. Now, usually this CL value is considered often for assessing the climb of a general aviation aircraft, and therefore, this is a significant operating point, and a substantial increase in L by D indicates that this airfoil has a superior performance in that regime. So, this was one of the more modern developments, and by this era computational fluid dynamics had developed significantly, and that helped to refine the designs further and optimize to a much larger extent than purely through experimental exercise. High speed airfoils have also been developed in the past several decades, and a very important development came through the so called supercritical airfoils. Again, many of them developed by NASA, and they are meant for increasing the drag divergence Mach number. This is something that we will learn later when we look at high speed aerodynamics. That means, the idea is the drag increase due to shock wave formation occurs at a higher free stream Mach number for these kind of airfoils. Which is an obvious advantage in high speed flows. We will discuss more on this later on, and we will discuss more on airfoil characteristics. Apart from CL alpha curve, we will also look at the variation of drag with angle of attack or variation of pitching moment with angle of attack subsequently. So, in this lecture we discussed mainly about pressure distribution on an airfoil, and airfoil nomenclature was discussed in detail, and then we discussed a little bit about variation of lift with angle of attack once again, but we will discuss more about how drag and pitching moment varies with angle of attack in the upcoming lectures. Thank you.